molecular orbital diagrams. And I shouldn't say sadly, because this is fun. This is where we really get to understand kind of the punchline for this whole chapter. I hope you might have been asking yourselves this key question right here that's in italics. Why is that Huckel number magical? 4n plus 2. Why is that so stable? Why is 4n unstable? What is so special about 4n plus 2? And what is wrong with 4n? Both pi systems are conjugated. We learned that conjugation is supposed to make things more stable, but we've just been told that anti-aromatic systems are very unstable. We have not answered that or addressed that yet, and we can't unless we look at the molecular orbital theory. So the molecular orbital diagrams will be the key to understanding what's going on. So we dive down that deep when we have to get an answer like that, right? We have to see what are the electrons doing, because whatever energy level they're at is going to explain their relative stabilities. So are you ready? I'm going to have you remind you of something before we dive in. It's really, we're really only looking at frontier orbitals, so it's not as complicated as it could be. If you go back to your general chemistry books, you know you did those whole things all the way down to core electrons, and we're only looking at what's at the outer shell. But focus is on conjugated pi systems and their molecular orbitals, so we're really looking at the electrons that were occupying p orbitals, so the pi system. And so focusing on the p orbitals, I want to remind you how they can add constructively and destructively. Because remember, they actually represent simplistic forms of wave functions. So if you were to take quantum mechanics, you would actually see that that p orbital, I'm going to draw it right here, is nothing more than a probability density map resulting from an equation that was solved. So it's not really a tangible object. It's a probability distribution, like the probability of finding an electron in space. So we know that probability is distributed across this map. We can call one px and another one py. Actually, no, that's not going to be a good idea, because I'm mixing the two of the same orientation orbitals. They have to overlap side to side. And remember, when we use a px and a py, we're talking about them being perpendicular. So let's say I have molecule A, and it's going to make a pi bond or conjugate with molecule B. They need to be side to side. So we'll call it PA and PB, both of which will be an X. If it's an X and an A, it's an X and a B. Okay? If it's a Y and an A, it's a Y and a B. So that part, don't worry about. Just they need to be parallel. So we have one p orbital for molecule A and one p orbital for molecule B. Now let's show how they can add two different ways to mix. It depends on their phases. So if we have them in phase, they're matching, all right? And what we're going to see is that we'll actually have, remember there's always a node right here. So PA plus PB. So they can add constructively because they're in the same phase. The dark lobe and the dark lobe are next to each other, and we're going to add them and mix them. So the dark's there. We always have the same nodal plane. All p orbitals have that node right there. So there's our nodal plane. That didn't increase the nodes. And then we have our kind of smeared together blended p orbitals in the bottom to make our new molecular orbitals. So pi MO. That's a constructive way to add them, because you actually made a bigger orbital, bigger molecular orbital. But if they're out of phase, that's another way we can add them. Keep that one up and have them add opposite. PA, that would be PA minus PB. Right? So if we do that, then we're actually, so we already have the nodes here. So we're always going to have this one. But we introduced a new node there because they don't add, they can't add that in that spot. So they're going to stay in their isolated nodal planes like that. So this one has more nodes. This one's actually the higher energy one. This is the pi star. So maybe I should have switched it, but just that's to give you an idea. That's destructive addition, because these are technically waves, and when you add wave functions, you're talking about constructive and destructive addition, or so it's basically subtraction. Okay, so keep that in mind, because we're talking about how those weird molecular orbitals look after we mix the p orbitals, and that's on account of constructive or destructive addition. All right, so how are we gonna, we've done this in conjugated pi systems. So like butadiene, for example, we've done the molecular orbital diagram for that. How does this look in a ring system with aromaticity? Let's use something called a Frost diagram to help us with that. Okay, so Frost diagram's used as a template just to kind of help us properly line up the orbitals. So it's a tool so that you can draw it properly. The rules for the Frost diagram is that the polygon, whatever ring you have, so you have a cyclopentane, cyclohexane, the vertex needs, one vertex needs to point down. That's going to allow only one level to be the lowest energy level. So steps for drawing a Frost diagram: you're going to make a circle. You're going to inscribe the polygon that's applied. So cyclobutane, you're going to make a square. Cyclohexane, you're going to make a hexagon. Okay, inscribe it. So that means only the vertices touch the circle, and you have to have one vertex down. Then you're going to use that template to make the MO diagram. Then you're going to keep going your way through the MO diagram. So let's follow these steps. I think it makes more sense in context. So we're going to do two. The ones that we know, we already know this was anti-aromatic, 4N, right? Because we want to answer that question. Remember, that's the goal. And we're going to use the Frost diagram to get to an MO diagram. And I hope that tells us our answer. 4N plus 2, aromatic. So benzene we know is aromatic. We know cyclobutadiene was kind of one of our token examples of an anti-aromatic pi system. And we want to know why is there a difference in stability, unstable versus stable. All right, so let's start by drawing the Frost diagram. So that means first we start with a circle. And I'm going to draw my square, right? It's a cyclobutane ring. I'm not worried about where the pi bonds are. I'm inscribing it in the circle with one vertex down. So here's my Frost diagram. Okay, so notice I have one vertex down. So I'm following this list. Draw a circle, inscribe with only one vertex down. Done, done. Now we're going to use that to help us sketch an MO diagram in which each vertex represents an energy level. So in other words, it's going to look like this. That's going to be an energy level. You're going to have a line at each vertex. And you're going to have a dashed line exactly halfway across the MO diagram, like that. Then above the line, we'll have our antibonding. Below the line, we'll have bonding. And if anything's on the line, it'll be non-bonding. Now let's use that Frost diagram, remove the circle and the polygon. And what we'll have left is the energy levels we need to make the MO diagram. Okay, so take the circle away, take the blue square away, keep only the energy levels. Looks like this now. So those were where all my vertices were. My green line I'm going to use to go halfway exactly down the middle. So above the line is bonding. Excuse me, anti-bonding, high energy. Below the line is bonding. And on the line is non-bonding. So we haven't seen that yet. That's new to us. So this is our energy. Now we fill up. How many pi electrons do we have? 4 pi. Fill up from bottom to the top. 2 in the bonding. Remember, bonding orbitals promote bonding. That's exactly why they're called that. They encourage bonding. Bonding encourages stability, keeps the molecule together. Non-bonding doesn't promote or discourage bonding. Anti-bonding encourages bond breaking. So that would be an unstable situation. So notice what we have here. We have 2 degenerate orbitals. So these 2 are degenerate. What does that mean? Same energy level. So we always pair last according to Hund's rule back in general chemistry. So we're not going to do this. We're going to put one parallel spin in each orbital. Now let's compare that to what happens in the case with benzene. Benzene as drawn, sometimes it's drawn this way. Whatever you end up doing, you need to rotate it so you have one vertex on the bottom. So just like that, just like it was actually already drawn. And if I draw the circle after, it looks very sloppy. So I'm gonna actually go ahead and draw the circle first. I know that from experience because inscribing a circle, drawing the circle to be inscribed around that polygon is harder than inscribing the polygon itself. Now I'm gonna draw the benzene with one vertex pointing down and all vertices touching the, oops, I made an extra line there. There we go. Okay. Yes, it's not beautiful, but I'm not going to go get a compass out to draw a perfect circle. You know, you get the idea, hopefully, that the whole point of that was to be able to draw these energy levels right here. And then you draw that line halfway through, and then remove the template. You got your energy diagram. So when you remove the template, we get over here, energy up, and we have this scenario with one on the bottom, two degenerate, one at the top. Line exactly down the middle. Nothing falls on this line. Therefore, we have zero non-bonding. We have only bonding and anti-bonding. How many pi electrons does benzene have? We know this, 6 pi, right? Time to fill it up. Bottom to top, pair, degenerate only when it needs to be full. So one on each, but that's 4 pi. We need to do to 6, 5, 6. Whoa, here we go. Take a minute to look at these orbital diagrams. That's the answer. We see the answer? What is our conclusion about 4n versus 4n plus 2 pi systems? So here's an example of 4n pi system. Here's an example of 4n plus 2. What do we know about unpaired electrons? Very unstable. So let's compare these right here and write our conclusion statement. Yes, black will do, I guess. So 4n plus 2 versus 4n. In 4n plus 2, we observed filled, paired electrons, in other words, in bonding orbitals only. In the 4n system, in the 4n pi system, electrons occupy non-bonding. So in other words, it's not as favorable as occupying a bonding molecular orbital. Furthermore, even worse, we have some unpaired electrons. So that means it's less stable. Not stable. Finally, we have our answer. You don't have to take Huckel's rule for granted. You can prove it with the molecular orbital diagram. So nomenclature for aromatic pi systems. It's pretty straightforward. There's a few commonly named, which means like a nickname instead of their systematic name. Aromatic pi systems we see so frequently that it's worth being aware of their names. So these are the ones you'll want to know. They all are mono-substituted benzenes, which means they have one group on them. Aniline, we brought up, has its own nickname. It really plays a big role in the dye industry, right? So that's where you'll see the aniline name come up. Toluene, we've seen many times before. It's just a benzene ring with a methyl group. So you could leave it as is, or you could write that methyl in. That's often responsible for that smell that a lot of people may or may not like, and markers, like permanent markers. But it's found in ointments as well. Like if you look at the ingredient list on something like Bengay, it has toluene, and it's extracted from the tolu tree. So that's where it gets that common name instead of its systematic name. Phenol, we've seen that one before. It means phenyl is sometimes what we use to refer to a benzene substituent. And then -ol is the prefix for alcohol. So that means we have alcohol in a benzene ring. Benzoic acid means we have the carboxylic acid on a benzene ring. Anisole. So that's a common monosubstituted benzene with a different functional group. Anise is named from like dill, the Greek word for dill, because it's been extracted from that, but it's found in other places as well, other natural products. It's the ether, the methyl ether on benzene. And then acetophenone, so it's like phen means we have the phenyl piece, acetone means like we have an acetone practically on with a phenyl replacing one of the methyls. So remember that's acetone. So acetophenone would just mean that we replaced one of the methyls with a pH. So that's what this is. So So acetone would be CH3. Let's just go back. So I could actually put that here. There we go. Acetone would be CH3, but if you replace the CH3 with the pH, then you have acetophenone. Speaking of the pH, so that's the phenyl is abbreviated pH. You will sometimes also see other ways to abbreviate a substituent. Benzyl has a BN. And then just plain old benzene. So benzene's a molecule. A standalone molecule, not a substituent. So you could say you have a benzene moiety. Moiety is a fun word. It means you have a piece of the whole component of the large structure has that component in it. So if you have to say you have a benzene moiety, it means that you found a benzene part, or if you could like circle a benzene ring in a bigger structure, but we still don't refer to it as a substituent. If we are referring to it as a substituent, you might see one of two ways. So benzyl actually means we don't just have benzene, but we have this CH2 here. It has to be there. So benzyl is this whole piece. Okay, have to have that CH2. So you might actually, it's actually a reactive H. We could take it off. It's pretty acidic because of that resonance that it gives. So we might say that benzylic H. What do we know about benzylic protons, right? So being adjacent to an aromatic ring with conjugation, it can actually delocalize it, so it makes it actually more acidic. Phenyl. Phenyl means we are not defining what's on the other side of that. So in other words, this would be a phenyl group, but if that group happens to have a CH2, we change the name to benzyl. Okay, so you want to keep those straight because we will be using them more often now that we're in the aromatic chapter. When we're naming, other things that are convenient is to have common names of substituents. So I'm just bringing that, this is old stuff, but I'm reminding you. Isopropyl, remember that's this piece. Tert-butyl, so that squiggly line means the rest of the molecule isn't shown, right? So tert-butyl. What else do we have? Isopentyl, sometimes even called isoamyl. And sec-butyl. So it's another way to arrange the, so think about this. We have 1, 2, 3, 4 carbons. That's tert-butyl. Isopentyl has 1, 2, 3, 4. 1, 2, 3. That's actually isobutyl. Glad I caught that. So that's isobutyl. Let's fix this to be isopentyl. Extra carbon. Isobutyl is worth pointing out. So it's isopropyl with an extra carbon. Isopentyl has 2 extra carbons to the isopropyl. And then the sec-butyl is the other way. That's what I always remembered because it's a weird shape. The other way to get a butane chain, we have the N-butyl, which means no branching, isobutyl, tert-butyl. And the other way we could do it is take this methyl, and instead of having it at the end, have it on the second carbon. So that's sec-butyl. And so right at that carbon there instead of the terminal carbon. Okay. Now I think we're ready. Now when we're going to encounter an organic molecule and we want to name it, a couple things to keep in mind. If there's only one group added to a benzene ring, we name that group as the substituent. But if we see like a really large molecule and benzene is also attached, even if it's a monosubstituted benzene, it might be hard to name the substituent. So if it's hard to name the substituent, then we call benzene a substituent and call it a phenyl. So you have to pick what's easier to name. And sometimes there's two ways to name it. That's why you'll see synonymous names for some things. So for example, phenyl versus pH, and we could have that branch off. So let's get into some examples. So these are the most common ways of naming benzene. This is pretty simple. Monosubstituted, benzene's the parent, and chlorine's the substituent. So we say chlorobenzene. So we're going to keep benzene as the parent if that makes it easier on us. So notice that we know this common name. You could actually name it systematically as well. Like you call this 1, 2, 3 carbons and call that a 3-carbon chain. And we could call it a propane parent. And we could say 2-phenyl propane. But we know a common name for this, and we call that isopropyl. So we could also call it iso, which could have a little I, or propyl benzene. Or you could just write out the iso. So I is an abbreviation for iso. Okay, here's an example where the branching might get a little difficult. So instead of having 2 different names for it, we're going to name the parent name because there's so much branching. So you want to give the highest priority group number 1, that carbon gets number 1, and it has, out of everything here, we have, so if we look at our parent chain, we have 1, 2, 3, 4. So because I don't know the name of this funky branch thing, I'm going to name the parent chain and call benzene a substituent. That's the pH. So I'm going to give carbon 1 to the carbon with the phenyl on it, 2, 3, 4. And that means I have to have a phenyl at my carbon 1, and that's implied. So you don't usually have to write the number 1. You can. It's just overkill usually. Carbon 2, I have a methyl, and at 3, I have a methyl. So remember, when we have 2 methyls, we call it a dimethyl. So it's a butane parent. So start writing that out. I always like to write the parent first, so I give myself some space. Substituents. I have dimethyl, so methyl, and I have phenyl. Well, methyl is M. We do this in ABC order. Phenyl is P. M comes before P, so dimethyl is named first, then phenyl. So it's phenylbutane. Where's that phenyl? At carbon 1. And then the dimethyl, we have to describe at carbon 2 and 3. 2, I didn't give myself enough space apparently. Dimethyl, 1-phenyl, but you might even see the 1 dropped. You could also call it dimethyl phenylbutane because it's implied that the highest priority group is on carbon 1. Okay, let's step it up a notch and name something with 3 substituents. How are we going to do that? Now, we have to find our highest priority group. So the priorities established who the parent is, and the fact that we have a benzene ring. If we want to have the name as a benzene parent, then notice we have fluoro, bromo, and amino. So amino, out of those 3, has the highest priority. And we've gone over this list before. It's in your reader if you need to go reference that. So we would say, okay, that's the highest priority. That has to have carbon 1. And how are we going to number? Go 1, 2, 3, 4, 5, 6. Or we could go around the other way. Once I know who 1 is, I just have 2 other options from there for numbering. But 1 will be the correct way. 1, 2, 3, 4, 5, 6. So my outcome would be a 1 with a red path, a 1, 2, 5 substituent pattern. My blue path would give me a 1, 3, 6 substituent pattern. Who wins? You got it? I hope, red. Well, the smaller numbers are gonna win. So 1, 2, 5. So I'm gonna get rid of this one. We're gonna go this route. Okay, there are two names, but there's an easier of the two. So notice that at carbon 1 is part of an aniline unit. So now we could just name it at the 2 and 3 position. Excuse me, the 2 and 5 position. So this would be called 2 fluoro, 5 bromo aniline. Or would I put 5 bromo, 2 fluoro? And this is often a common multiple choice type question. Which one of those wins? Remember, once you assign numbers, you don't put it in numeric order, you put it in ABC order. So ABC order is this one. That's the preferred name because it's the simpler name. The alternative name would be to name all positions, 1, 2, and 5, and it'd be amino benzene. So we'd say 5 bromo, 2 fluoro. Instead of saying aniline, we'd say amino benzene would mean that we left benzene as the parent, or benzene amine, right? Those are kind of sometimes interchangeable. But since we're using benzene as a parent, I'll say amino benzene. But we might also see benzene amine. And the E's dropped because look at those two vowels together. It can get complicated with what's italics, what's not. My biggest concern with IUPAC naming, you can have a thick book with rules that feel like they don't end. And to be honest, at a certain point, I got to look them up myself to make sure I'm going to the right route. But the goal of the IUPAC systematic naming is that we draw the same structure. So if I were to tell you this actual structure, there'd be no ambiguity. So if I tell you this name, you can draw the structure. If I tell you this name, you can draw the structure. Same with the one before. And so the stuff that comes after that, like whether it's italicized or hyphenated, I'm not as concerned about. It's more that keeps it kind of neat and tidy to separate the pieces. But most importantly, we want to be able to pick, if it's multiple choice, the correct name, or to name it in a way that's unambiguous. Okay, so other scenario that has its own special naming category is the disubstituted benzene rings. So notice the pattern. When you have two substituents on a benzene ring, we have these possibilities. So let's give one of them position 1, X, and then we have something coming off. And notice how it looks like that bond's coming out of the middle of the ring. That means we're not defining whether it's a 1, 2 pattern, right? So Y could be at number 2. So we'll call that a 1, 2 pattern. Y could be at the 3 position, 1, 3 pattern, or Y could be at the 4 position, and that'd be a 1, 4 pattern. And notice that that repeats. If I go to carbon 5, that's the same thing as having it as X at the 1 and Y at the 3. And if I go to carbon 6, that's the same as a 1, 2 pattern. So there's only 3 possibilities in a disubstituted benzene ring. So the 1, 2 position has its nickname ortho. So there's 2 names. You could either call it 1, 2 dichlorobenzene, I misspelled that, chlorobenzene, or we could call it ortho dichlorobenzene. And that's usually italicized because it's a Greek root. Greek for correct. They're the ones adjacent to each other. You'll even see a little O abbreviated. It's usually in italics. So a little O. So sometimes I try to write it a little bit cursive to look italics. Sorry, I think I forgot. I want to misspell chloro for some reason, while I'm talking, chlorobenzene. There we go. All right, so The most common way you'll actually see it is ortho instead of the 1-2. So likewise with 1-3, it has its own nickname of meta. And so the 1-3 position, we meta, and I used to remember that by thinking like, oh, this looks kind of like an M right there, right? An upside down M. Whatever it takes. Meta, or M, dichlorobenzene. And then if they're at the 1-4 position, that's called para, when they're on opposite sides. I think that it comes from the Greek word similar, but I think that's because it introduces that symmetry, right? You get a plane of symmetry once you have the para position. So little p, para, dichlorobenzene. So before we go on, I might leave you with a little humor. What would you call? Let's do an MD. Some people are going for those MD and PhD. Well, there's two doctors that are para to each other, so you have a paradox. Ha ha ha. You could do the orthodox as well, right? I'll leave that one for you. Study and practice, years of it.